important. A little brief about Peter is last year when we did the Ghana Numerical Analysis Day, I had a message from Peter, and he told me I'll be very happy to present at Ghana Numerical Analysis Day. And then when he presented, he gave us a brief of a history of why he was very happy to present at the Ghana Numerical Analysis Day. Maybe today he can also share it for a lot of the listeners to get a little bit idea of who Peter is. Peter, he did his master's, Oxford, PhD, has been in Oxford, Cambridge, and UCLA, right? And no,
yeah.
Imperial College as well, and then now also at MIT, and doing they're currently at MIT. So we are very, very privileged to have Peter give us a talk on physics-informed methods. All right, thank you.
Thank you, Stephen, for the introduction, also for the invitation to share this research with you. Yeah, I'm really honored to be able to speak to the Ghana numerical analysis community. And I can sort of echo Stephen's comments about computational math. And closely related to computational math is, of course, computer science. And here at MIT, over a third of all undergraduates are majoring in computer science, largely because they recognize the importance of these computational methods, especially as they pertain to data science and machine learning, which is a really, obviously a very hot topic at the moment, and is and the field is looking for lots of employees, so it's a very employable field too. So I would really welcome any questions or comments anytime. So we can make this quite interactive, and if you have any questions at any point, just say. You don't have to write it in the chat if you don't want to. You can just unmute and start talking, and we can chat about things and work through things together. So this is a project, as you can see, between myself, Benjamin Herman, Beverly McKeon, Nathan Kutz, and Steve Brunton. And the topic is this physics-informed dynamic mode decomposition. And this area lies in the field of data-driven methods. And we're specifically interested in learning these dynamical systems from data. So the traditional paradigm of analyzing dynamical systems has been to derive the dynamical system itself from, say, first principles, usually from conservation laws like conservation of energy or conservation of momentum. And we can exploit those principles to derive differential or partial differential equations that characterize the system. But in this data-driven age, many researchers are moving from a theory-driven approach to a data-driven approach, where instead of using first principles to derive dynamical systems, we try to derive them from data. And that could be advantageous because you might be studying a system where there aren't known conservation laws, or at least there's uncertainty in the conservation laws. And another reason might be that we might want to try and infer a simpler model for something like the Navier-Stokes equations in this case, and we can use data to infer that effective model. So we probably all know that like solving the full Navier-Stokes equations is extremely challenging, but in many fluid dynamic situations, the vast majority of the flow behavior is characterized by some coherent and persistent patterns. So you can see in this flow past the cylinder on the far left, even though the Navier-Stokes equation is very complicated, the solution of this PDE has some clear behavior. So can we analyze that behavior to find a simpler solution and a simpler model? So the question is, can we find a function that approximates the true dynamical system? And can we find that function just from data measurements of the system? And there are various techniques to do that. I just listed 4 here. And the aim of these techniques is to achieve various engineering tasks. So here I've listed 3, so modeling, prediction and control. So we might want to be able to like control this fluid dynamical system to achieve some engineering goals, such as drag reduction. But at a scientific level, we might not be satisfied with just these engineering goals. We might also want to obtain some understanding, some physical understanding of the system. Okay. So the way that I motivate this method is through this clip from this movie Dumbo, which apparently was one of my favorite movies growing up. And in the opening scene of Dumbo, we see this flock of storks delivering newborn babies to expecting parents. And in folklore all around the world, the white stork is a picture of reproduction and new life. And I suppose that part of the reason that we have the story about these storks is that it allows parents to avoid difficult conversations with their children about where the children came from. Yeah. So you see here, this baby bear's been dropped off and it's meeting their parent. Does someone have a question? No? Okay. And yeah, so we have this story about the stork, and it's so that we can avoid difficult conversations about how these children were created. So when we use this analogy, we're being a bit disingenuous. We're acting as if we don't really know where the children came from. And there's now an analogy with data science and data-driven methods, which is that when using many machine learning and data-driven techniques, we can act as if we don't know where the data came from or where the data was, or how the data was generated. So in this picture, the parent bear is the data scientist, and they're so excited to receive this clean data that they forget or they don't care how the data was given to them. And this seems like a missed opportunity because knowing how the data was generated can provide us with a lot of extra information. So we might know that there are some conservation laws that the system satisfies. So this is a fluid mechanics system, and we might know that conservation of momentum is valid. So the goal of this talk is seeing how we can leverage that knowledge of how the data was generated to improve data-driven algorithms. So this is the goal. How can we exploit that knowledge of the physics of the system, those being symmetries, invariances, conservation laws, and how can we use those features to improve data-driven techniques? Okay. And this is obviously definitely not my idea. This has been applied to many machine learning methods already. So here I'm illustrating just 4. You may have heard of these physics-informed neural networks, which have really taken the computational world by storm and have been very popular and very successful. So in this case, one trains a neural network that is penalized by departures from the known physics. And you can use this to identify PDEs and also solve PDEs and identify hidden features. There's also sparse regression techniques where we seek a model for our system that is sparse in a certain basis so that it can be interpretable. And today we're applying this principle of incorporating physical laws, and we're applying it to something called the dynamic mode decomposition, which is a specific type of data-driven technique. And I'm going to tell you about that modal decomposition. But just as a taster of what's to come, here's a slide that compares the normal dynamic mode decomposition with our new physics-informed dynamic mode decomposition. So in this case, we're studying just the simplest partial differential equation, but we only have, which is the advection equation. So it just corresponds to a translating wave or translating pulse. And we only have access to an incomplete data set. So we've only sampled our system over a short time period. And in this case, if we train a model using other DMD methods, then we get a very poor prediction. Whereas if we tell the model that there is some symmetry in the system, specifically that it is shift invariant, then we're able to obtain a much more accurate prediction of the future. So I'm going to explain how this DMD algorithm works. So we are studying a system of which we have measurements. we have snapshots of that system at various points in space and time. So for example, if we look at this situation on the left, we could have some function u of psi t. And when we evaluate this function at certain points, we end up with a vector of those evaluations. So this u of psi t might be, say, the fluid velocity at points in space and time. It might be like the percentage of infected individuals in an epidemiological model, or it might be some other physical process like in quantum mechanics or plasma physics. But we don't know this function at every point in space and time because we're on a finite world, and we're doing things on a computer. So all we can do is sample this function at a few points in space and time. So throughout this talk, we're going to use the notation bold X to represent a vector, which is the state U evaluated at different points in space and time. So X here is not a spatial coordinate, but it's a state vector of evaluations of the function that we're studying. Okay. So this X is really all that we have access to. We only know U at these discrete grid points. Okay. And we also take pictures of our function at a bunch of different times. So we take m different pictures, and that gives us m different vectors. And we use the subscript k to represent the time at which this state vector is evaluated. And one thing we can do is not just look at u at a specific time, but we can also look at u advanced forwards in time by a certain amount. And we can do the same procedure and get a set of m measurements. And the key behind DMD is that these measurements at xk plus 1 are related to the measurements at xk via just a linear relation. So this is a big assumption of DMD, that it assumes that underlying the system, there's a linear operator, or at least the system can be well approximated by a purely linear operator. So this is like the really important equation. These xk's are data measurements. They're snapshots of the system that we have. And A is an unknown matrix. And the key behind DMD is inferring properties from this matrix. Inferring properties of this matrix from the data. So specifically, DMD exploits features of this linear operator that best represent the data. And it uses those features to decompose the data into something that is very interpretable. And we'll see that interpretability in just a moment.
Hi, Peter.
Hey.
Can I interject, please? I just want to be clear with this. So the key idea is the matrix decomposition, right?
Yeah, so
okay.
What we're going to do is like try and find a good A that well approximates the data and then decompose that A. And then that's going to help us decompose the data matrix. Yeah, you're exactly right.
Thank you.
Okay. Yeah. Keep asking questions if anyone has any confusion or wants any clarification on anything. Okay. So yeah, this is the really important equation, that we have these data measurements, and we're going to try and find a matrix that approximately propagates these measurements forward in time. So this xk is the xk. So xk plus 1 is the xk advanced forward in time. And we want to find how it's advanced forward. One issue might be that we've used this approximation sign, and that's not necessarily a well-defined relation. So I'll talk briefly about what this approximation means. So when we say that A of xk is approximately equal to A of x of k plus 1, we mean this in the sense of energy. So we mean that the energy of x of k plus 1 should be approximately equal to A of x k. Oh, sorry, I really mean like the difference of the energy of these things. So yeah, that'll become clear when we go on this side. But if we just focus on this for now, we assume that the energy of this state can be represented as the L2 integral of the system U. And when we only have access to measurements of U at discrete points in space, Well, we need to represent this continuous integral as a discrete quadrature. So here we're saying that the energy of the state x is just given by this summation. And we might need to include some weighting matrix that accounts for maybe certain physical scalings or the quadrature like grid points. But we can always, provided W is a positive definite, we can always rescale things such that the energy of the state is the 2 norm. So whenever we see the 2 norm of a state, we should think of its energy. And then when we want to find an A that approximately propagates these measurements forward in time, we want it to do so such that the energy of the errors of that propagation are small. So by that, we mean that if we sum up the errors between all our measurements and the propagated measurements, then we want that, that sum to be small. So here we're saying that the difference between x of k plus 1 and a of xk should be minimized. So another way of thinking about this is that this is the reconstruction error of our model A. So A is a model, it's going to be an n by n matrix, and A of xk is supposed to propagate the system forwards in time, but x of k plus 1 is what the system actually is propagated forwards in time. So these two things should be similar, and we want the difference between them to be small. So another way of phrasing this minimization over this sum is to just phrase it as a single minimization over a single norm, and this subscript f is the Frobenius norm. So this just means the sum of the squares of the elements of this matrix, and these are two data matrices. So the X matrix has columns of x1, x2, up to xm minus 1. And then the Y matrix is the same size, except the corresponding columns are the X columns, but advanced forward in time. So you can see that in Y, the second entry in Y is, the first entry in Y is the second entry in X. So you get from X to Y by moving forward in time. Okay, so that's, I butchered the explanation a little bit, but this is a really helpful picture. So this X matrix has all these different columns, and then the Y matrix has the same columns, but just shifted to the left. So here you can see we have this, this sort of green column, which is the second column of X, and in Y it's the first column. And then this brighter green one is the third column of X, and it's the second column of Y, and so on and so forth. So we want to find an A that minimizes this reconstruction error. And that's just this minimization here. And this might look familiar because this looks very close to a linear least squares problem. So usually least squares problems are of the form AX minus B, and we know A and we know B, and we're trying to find X. But in this situation, the problem is sort of reversed, because here we know Y and we know X, but we're trying to find A. So the argument just means that we're trying to find the A that minimizes this difference. So it's basically linear least squares. And there's an exact solution for this minimization problem in terms of the Moore-Penrose pseudo-inverse. So as we know, not every matrix has an inverse, especially rectangular matrices, but every matrix does have a pseudo-inverse, which is in a sense the closest thing you can get to an actual inverse. So that pseudo-inverse is denoted with this dagger symbol here. And the A that minimizes this error is just given by this YX pseudo-inverse. So once we've sort of constructed this solution, at least symbolically, we can then do various engineering tasks, like we can try and reconstruct the data in a lower dimensional way. We can do prediction. We can look at diagnostics and stability. And by far the most common and like the original formulation of the dynamic mode decomposition is to look at the eigenvalues and eigenvectors of this matrix A. So in practice, because the systems that we're studying are very large, it's more usual to project this, this high dimensional A into a lower dimensional subspace. And then from that, you can do an eigen decomposition. So find the eigenvectors and eigenvalues. And then we'll see on the next slide that you can use that decomposition to decompose your data. Okay. So the original formulation of DMD was for dimensionality reduction. So by that, we mean that we might have some very high dimensional data, like from a fluid mechanics simulation, I mean, many situations in data science, especially the physical sciences, where we have simulations with millions or billions of degrees of freedom. We might want to reduce that complicated data set into just a few important structures, a few modes, you might say. And DMD provides a spatio-temporally coherent way of doing that. So we can use that eigen decomposition that we found on the previous slide to decompose our data. So the first step is to take our first measurement and represent that as a linear combination of the eigenvectors. So this phi was just it's just a matrix, and each column in phi is an eigenvector. So we take our first measurement and we represent it as a linear combination of those eigenvectors. We then take the second measurement, but we know that the second measurement is at least approximately A times the first measurement. So we solved this optimization problem where we found an A that approximately maps the xk onto the xk plus 1. So these two things should be close. But then we can substitute in our representation for x1 on the previous line. But then remember that this phi matrix is a matrix of eigenvectors. So A times phi is just phi times lambda. Lambda is the matrix of eigenvalues. And we can consider that process indefinitely. And you can represent any measurement, xk, in this form. So the eigenvectors times a power of the eigenvalues times this w. And the w is just a vector that corresponds to how much of each eigenvector is in the initial measurement. So this is really valuable because it shows you not only the spatial dependence of the system through these phis, but also how the system evolves in time. So we'll know that when we're studying linear systems, like linear dynamical systems, it's sufficient to understand the eigenvectors and eigenvalues of your system in order to characterize its behavior and find all the solutions of that system. And here we're exploiting a similar phenomenon. So given that we can do this, this representation for any measurement xk, we can then represent the full data matrix X in this decomposed form. So this might be what Thomas was asking about earlier, that this is a decomposition of the data into some very interpretable structures. So this first green matrix is the mode matrix. So these are the eigenvectors, phi1, phi2, etc. The eigenvectors of that matrix A. And then there's this diagonal matrix, which is just how much of each eigenvector is in the data. And then this last matrix, this van der Waals matrix, represents the temporal evolution of the system. So this might be reminiscent of the singular value decomposition, where you take a data matrix and you break it down into one orthogonal matrix, a diagonal matrix, and another orthogonal matrix. And this is clearly very similar, except there's no requirement that phi and this dynamics matrix need to be orthogonal. And the original development of DMD was to allow for eigenvectors that are not necessarily orthogonal to each other. So I'm just going to sum up that introduction to DMD before I talk about our own extensions. So this slide just shows a classical application to the flow past a cylinder. We have a system and we have measurements of that system. in this case, the flow field, the vorticity field. And we have measurements at a bunch of points in space and a bunch of points in time. So even though this solution is 2D, we can flatten the system to make it into a really tall and skinny vector like x1 or x2. Then we said that we can approximately model this as a linear system of xk plus 1 approximately equal to a times xk. That led us to this minimization problem, which we could solve with the more Penrose pseudo-inverse. And we can also get a low-dimensional approximation of that system. And then having done that regression, we can then perform some diagnostic tasks like extracting the dynamic modes of the data and looking at their time dynamics. So this technique has been applied to lots of different areas. You can see that I listed 5 here. And it was originally developed for fluid mechanics. And there's a great review in the annual review of fluid mechanics by Peter Schmid. And Peter Schmid was the original developer, inventor, discoverer of DMD back in 2010. So maybe I can have a couple of questions now before I move on to the next part of the talk. So does anyone have any questions about what I've talked about so far?
Hi, Peter. This is Thomas.
Hi, Thomas.
Hi. So far, so good. I think your talk is great.
Okay.
Want to know what's the difference between this approach and the Cindy approach?
Yeah, great question. So I have a slide, I think, on Cindy. So Thomas is asking about a method of sparse identification of nonlinear dynamics.
Yes.
Let me see if I have a slide on that. No, I don't think I do. But in that method, one seeks to find not necessarily a linear system like we did here, but a non-linear system that's sparse. So yeah, Cindy, developed by my collaborator Steve Brunton, and it's suitable for nonlinear systems, but it struggles with high-dimensional systems.
High-dimensional systems. Oh, okay.
Yeah.
Okay.
Although there's like various techniques of trying to deal with that.
Yeah, I research with piDMD a lot, and there have been variants of piDMD and depot nets and stuff like that. But I'm curious because I think that dynamic mode decomposition also offers some sort of advantages to modeling these nonlinear systems. So I'm curious what is the main addition that physics brings into the with combination with the DMD? I know you said it helps in overall the accuracy of the prediction, but what other additional advantage does the piDMD combined with DMD brings to the table?
So I don't know about many approaches that are combining physics-informed neural networks with DMD. So I have seen approaches that combine DMD with like a standard neural network, and their goal is to the neural network is an autoencoder in that case. So it tries to find like a lower dimensional nonlinear representation of the data that is linear in time. So then you have this like autoencoder that starts very big and then gets small, and then there's like a linear piece in the middle. So that's connected to this thing called Koopman analysis, which is like the bridge between this linear DMD and nonlinear systems.
Gotcha.
So yeah, in this talk, I'm not using physics-informed neural networks, although I think there is a connection.
Okay. Yeah, something to look into in the future. Thank you.
Yeah, great. Any other question at this point? Okay, so I can move on and talk about what we've done to do with DMD. And as I've alluded to, we are incorporating physical laws into DMD. And yeah, like I mentioned, we actually do that without using neural networks. We have a simpler way that doesn't require such heavy techniques. Okay. So the key to notice is that DMD, as I've explained, it doesn't seek like the true minimizer of your optimization problem. It actually seeks a low rank matrix that minimizes this thing. And the reason is that these systems are very high dimensional. So actually pursuing the true minimizer is not really tractable because of because this A will have n squared entries, and n could be in the millions or billions. But these low-rank matrices can be represented in this form. So this is an n by n matrix, which we're representing as the product of an n by r matrix and an r by n matrix. So a matrix of rank r can be represented in this form as long as these pieces are linearly independent. And part of the motivation for seeking a low-rank matrix is that they're very interpretable. So if I just looked at this matrix, I probably can't tell you much about it. But if it's low rank, if its dimension is small, then I can look at those important dimensions, like these two columns and these two rows, and maybe I can understand that lower dimensional set instead of the full A. So these representations are very interpretable, and one could say that they're representative of modal physics. So that means here just that A can be characterized just by a few important modes. So here are a few important columns and rows. And because we can factorize these low rank matrices, they're also very efficient in terms of memory. So instead of storing n squared entries, I just need to store these two small submatrices. And for similar reasons, they're very fast to compute with. And these low-rank matrices have dominated a lot of the literature, and I mean, for good reason, because low-rank matrices really do a lot of what you want. But during this project, we noticed that low-rank matrices are not the only interesting or useful type of matrix, especially for studying physical systems. So there's a whole world of other matrices out there. I've illustrated just 6 here, and each of these matrices has very attractive physical properties. So for example, we might have a matrix A, which is symmetric, and that corresponds to self-adjoint physics. So if we're studying a linear self-adjoint system, then we can represent it as y equals ax, where A is a symmetric matrix. We might have a system that is shift invariant or translation invariant. And in that case, this matrix A should respect that shift invariance, and it should be circulant or Toeplitz or Hankel. So circulant just means a matrix that has constant diagonals with periodicity. And there's all other different types of physics that we can think about. And in this physics-informed version of DMD, we exchange this low rank constraint on our model. So that's this constraint that the rank of A has to be equal to R. We exchange that for this constraint that A lies in M. And this M is just a class of matrices. For example, if we know that our system is self-adjoint, we might say that M is the class of symmetric matrices. Or if we know that our system preserves energy, then we might say that A is the class of unitary matrices. So technically, M is a matrix manifold, technically a Riemannian submanifold embedded in the space of n by n matrices. But we actually don't need much of that the formal technology of matrix manifolds. But the take home of this slide is this, and really of the whole talk, which is that we incorporate these known physical laws into DMD by forcing the model to lie on this physics-informed manifold. So we're saying, okay, I know that this system is like local, I know it's causal, or I know it's shift invariant, I know one of those things. I'm going to use that knowledge in my optimization to obtain a better model. And hopefully that model is more robust to noise and is going to be more generalizable and will generalize to different data. So Olu Sola is just asking, can we have the soft copy? Yeah, I'll be able to share the slides with you guys. Okay. And we actually solve all of these optimization problems exactly. And by exactly, I mean just in terms of standard linear algebra objects. And that's very attractive because it means that we don't need an iterative algorithm, which could be quite slow for very high dimensional systems. And actually our algorithms, our exact solutions outperform the state of the art in matrix manifold optimization. And that's partly because this is a very specialized problem, so we can develop very specialized tools for it. So part of the reason we solve these problems exactly is that this problem is actually a very old problem. It goes all the way back to Greek mythology, to this character of Greek mythology called Procrustes. And in the legend or the myth of Procrustes, we learn that this character Procrustes was a bandit, and he lived on this road. And the road was very long, and there would be lots of travelers on it. And he would tell the travelers that he had a magical bed. And no matter what size the travelers were, they would magically fit onto his magical bed. So the travelers were usually really excited because they'd been traveling for a long time and they wanted to rest, and this bed sounded like it would be a perfect fit. But it turns out that when they went up to his house, the reason that they would fit on the bed every time is that Procrustes would either chop off their limbs, in this case, or amputate their limbs to force them to fit on the bed. So it's a bit of a grisly tale, but there's an analogy for each of these characters in the Procrustes legend in the optimization problem. And this optimization is called a Procrustes problem. It's been around in the statistical literature for since the 50s. And it seeks to find this A that's constrained to this manifold that best maps X onto Y. So the analogy with these characters is that this victim is the matrix X, the bed is the matrix Y, and A is the treatment that maps the victim onto the bed. So the treatment in the legend would be the amputation or the elongation of the limbs. So so there's an analogy between this optimization and this Procrustes legend. Okay, so there are a few solutions for this problem in the literature, but we also developed many of our own. I'm going to talk to you a bit about an application of this work. So this is a version of DMD that is energy preserving. So as I mentioned at the start, the assumption underlying a lot of DMD is that the 2 norm of our data corresponds to energy. And in the optimization, we try and minimize the difference between our data and its reconstruction as measured by that 2 norm. So if the energy of the 2 norm of the state, if the energy of the state is just its 2 norm, and we want our matrix to preserve energy, well, then we just need our model A to preserve the 2 norm of the state. So the 2 norm of xk should be the same as the 2 norm of A times xk. So geometrically, this just says that the length of the vector isn't changing. It's either being rotated or maybe reflected. And in matrix language, that means that this model A is unitary. So the transpose of A times A is just the identity. The columns and rows of A are orthogonal vectors. And this minimization problem is called the orthogonal Procrustes problem, and it was solved back in the 60s. And the solution for A, so the A that minimizes this error function, is just given in terms of the SVD of this function of the data. So this is a very tractable problem. We can compute this SVD easily, and we can get the A that minimizes this error subject to this model A being conservative. And we applied that principle to this problem where we're studying a nonlinear, a double pendulum. We're looking at the small amplitude regime. So this system is approximately linear. And if we neglect the effects of viscosity and air resistance, then this system is energy preserving. So we're going to train 2 models on this data. One model is just a standard DMD approach that doesn't know about the energy preserving aspect. And then the other is this physics-informed DMD that does know about energy conservation. So if we do that, and then we try and reconstruct our data from these noisy measurements, then the DMD model is very bad. It's very corrupted by noise, and the reconstruction is very inaccurate. Whereas this physics-informed DMD model is much more accurate. You can see it really gets the frequencies of these oscillations right. It occasionally underestimates or overestimates the frequency. But importantly, the error is sort of constant in time, because the piDMD knows that this system isn't decaying or blowing up. It just has a constant energy. We can apply a similar principle to studying the flow past a cylinder. And when it's on this limit cycle, the 2 norm of the state is approximately constant. And again, when it's noisy, our physics-informed DMD is able to learn the eigenvalues of the data, like learn the spectrum with much more accuracy than a standard DMD approach, which is corrupted by noise. So another big application area that we've looked at is this, is shift invariance. So by shift invariance, I mean that if we have a model, which is A, and we might not know how A behaves, but we might know that if we shift our input and we plug that into A, then we get the same output, but shifted by the same amount. So let me just go through that again, that we know that if we plug this xk in, this A, then we get a yk out that looks like this. And we might also know that if we, like from certain physical properties of the system or its geometry, we might know that if we shift the input and plug it into A, then we get the same output, but shifted by the same amount. So another way to phrase this is that A is a shift invariant matrix. Shifting the input is the same as shifting the output. And these shift invariant systems are typical of constant coefficient PDEs and integral equations of convolution type. And like physically, they represent homogeneous systems with no sort of boundary conditions, with no like translation variations. Okay. So we just argued that if your operator is shift invariant, then it should commute with the shift operator. So this is just saying that shifting the input is the same as shifting the output. The matrix interpretation of that problem is that the model is circulant. So as I mentioned earlier, circulant just means that the diagonals of the matrix are constant with periodicity. Okay. So now if we know that our system has this shift invariance, then we want to find the matrix A that minimizes our cost function subject to the model being shift invariant. So again, you can actually solve this problem by hand using fast Fourier transforms. So the first thing to note is that circulant matrices have a very nice structure. They are diagonalized by the discrete Fourier transform matrix. So all circulant matrices can be represented in this form, where F is the discrete Fourier transform matrix, and then A hat is an unknown vector of eigenvalues, a vector of unknown eigenvalues. Okay, so wherever we see A, we can then substitute in this, this F star diag A hat F. The next thing to note is that this DFT matrix is a unitary matrix, meaning it's just a reflection or a rotation. And importantly, this norm, this Frobenius norm, is invariant under unitary transformations. So that means that we can basically move this F star onto Y. And then the last step to note is that this Frobenius norm has a nice property, which is that we can separate all the different rows of the matrix that's inside the Frobenius norm. And the point of that is that we can then reduce this problem to just n one-dimensional regression problems. So I wrote the solution just in terms of the MATLAB notation with the / or backslash. And you can find all of these eigenvectors just by doing this type of one-dimensional regression. And physically, this just says that in shift invariant systems, the eigenfunctions are sines and cosines. And now we're just regressing onto the coefficients of those sines and cosines. And in terms of computational complexity, the complexity is very low because all of these matrix-matrix products can be computed very efficiently using fast Fourier transform methods. So we can outline the framework that we use to come up with this shift invariant DMD. The first step was to know something about the physics of the system. So in this case, it was that we know that the system is shift invariant. The second step was to take that physical understanding or intuition and convert that into a mathematical statement. So here it was that the shift operator commutes with the model. And then the next step was to translate that mathematical statement into a matrix statement. So here it was that the matrix A is circulant, it's periodic. And then the last step was to solve the optimization algorithm to find the A that minimizes this cost function. Okay. So here's an application of that shift invariant DMD. So we're learning this, this translation invariant PDE with the advection, diffusion, and advection diffusion equations. We're learning them from noisy measurements, and we're particularly interested in the spectrum of this, this operator, so its eigenvalues. And you can see that if we constrain the learned model to be shift invariant, then the learned eigenvalues are very accurate. You can see the crosses are right over the circles, whereas a DMD model that doesn't know about this shift invariant physics is very inaccurate. Okay. And we can do these same things with more complicated examples. So here we are plotting and simulating the three-dimensional Navier-Stokes equations. And we only have access to a few data measurements. But this problem would be really intractable because of those few measurements, because there are many unknowns in the system, but only 300 snapshots, only 300 measurements. But if we note that the system is shift invariant in two directions, meaning you can shift your observer up and down and to the left and right, and then the system doesn't change. So we can exploit that to design a physics-informed dynamic mode decomposition to extract the true modes of the system. Okay. So a standard DMD model would seek a low-rank representation of the model that best represents this data. Whereas a physics-informed model, in this case, given that we know that the system is shift invariant, this physics-informed model has this circulant structure, but in a block sense. So the blocks of this matrix are circulant, and that corresponds on these two levels to the two dimensions in which the system is shift invariant. And if we do that, then the learned spectrum of the system is relatively inaccurate. But if we constrain the model to respect the symmetries of the shift invariance, then the learned eigenvalues are much more accurate, especially in this regime where the eigenvalues are the least damped. Okay. So maybe I'll just skip this slide and show you another application where instead of incorporating like a symmetry or a conservation law, we here incorporate locality. So in this situation, we are forcing our physics-informed dynamic mode decomposition to respect the locality of the system. So that just means that the state at a given point depends only on the states in a small neighborhood of that point. And in matrix language, that corresponds to a tridiagonal or a quindiagonal or quadriagonal matrix. Just meaning that there's the diagonal and a few terms either side of the diagonal are non-zero. And in this case, if we incorporate that constraint, then we're able to learn the modes, in this case, the response and forcing modes, we're able to learn those with much more accuracy than a standard dynamic mode decomposition. Okay. One last detailed example, which is that DMD can also be applied to like quantum mechanics. And when we know that we're studying as a Hermitian operator, as arise in quantum mechanics, then we can constrain our model to respect that symmetry and learn much better representations for the eigenvalues from data. And then this slide shows a big summary of lots of the different areas that we looked at today. So we have all these different types of physical structures that correspond to different matrix structures. And we applied this idea of restricting the model to a certain matrix structure. We've applied that idea to a lot of different physical scenarios. So there's a lot on this slide. The thing I would just draw your attention to is that it's this column and this column, which is just that the standard DMD approach learns a relatively inaccurate, sometimes very inaccurate spectrum, whereas the physics-informed approach learns the spectrum that is much more accurate and closer to the true spectrum of the underlying PDE that generated the data. Okay, so just to sum up, we've presented this physics-informed dynamic mode decomposition, which is this new framework that allows us to leverage our knowledge of physical structures into this data-driven linear system identification, and it allows us to identify the modes that best characterize the data. And through a sequence of examples, we've demonstrated that piDMD is more generalizable because it knows about more of the structure of our system. It's less sensitive to noise, and it also requires less training data because there are fewer degrees of freedom in the system. And we derive the closed form solutions for many of these optimization problems, and they're all available actually on this GitHub. So future work should establish like deeper connections to these types of symmetries for nonlinear systems, and probably the gateway to that is going to be through Koopman theory, which has enjoyed a very strong connection to DMD. And then another approach could be to relax a bit this very strict constraint of A lying in this matrix space, but we could instead just penalize our model in terms of the distance from the matrix model A from our proposed physics manifold. So as I wrap up, I'll just comment on how I'm connected to Ghana and Ghana numerical analysis. So my heritage is that I'm 1/4 Ghanaian, and these are my grandparents. Dr. Michael Alase Baddoo, who is Ghanaian, and Mrs. Barbara Baddoo, who was British. And they have a very interesting story. It's actually in a book by my grandmother called To Ghana with Love. I should have included a picture of it. But they met during the Second World War when my grandmother was evacuated to Cambridge. And my grandfather was studying to be a medical doctor at Cambridge at the time. So yeah, I'm very grateful for the heritage that they've given me, and that it allows me to connect with Ghana and with the mathematics community. And I'm sure they'll be very proud to see how the community is really flourishing with things like AIMS and the Ghana numerical analysis community. They would be really happy to see that. So I'll wrap up there, and if you have any questions, I'm very happy to take them now. If you think of anything later, then you're free. I'd love to receive an email from you, and you can see more of my research both on my website and on this YouTube channel, where I have a few short video abstracts. So thanks for listening, and I'll be happy to take questions.
All right, thank you very much, Peter. This was really, really nice. Especially I like the slow pace